Okay, so we are looking at segment lengths today. And there's three additional, and these are the last three things that we need to learn about circles. But they're not about angles, they're about the lengths of segments. And what this first result states, wow, what happened there? Okay, what this first statement states is that if you have a circle with two chords that intersect, and they can intersect anywhere in the circle, you know, they cut each other not in half, but they cut each other. Each segment cuts each other into two segments or two segment lengths. And so if I say this small segment here is length x, and this other segment is length y, and then the other one's cut into maybe length a and length b, that if you actually knew what those numbers were and you multiplied a and b together, you get the same product as if you multiplied x and y together, no matter what. So it's kind of an interesting application. You take any two segments in a circle, make them cross, and wherever they cut each other, you could say that those one length times the other is equal to the product of the other two segments from the second chord. So where does this come from? Well, in the proof, we're going to use similar triangles to prove this. And we had, in Unit 6, we studied similar triangles. We didn't do lots of proofs with them, but there's so many applications and so many proofs that similar triangles can help us with. And so I'm gonna save this one for you to do because this is the easiest of the three. And I'm going to give you a hint right now that in our picture here, you can see the blue dotted line on my. So you want to show that triangle ADE is similar to triangle, let's see, what would we say? So I said ADE, that's a CBE. Okay, so this is a hint. And there are three different ways to show triangles similar that we studied. And what was the most used way? Angle, angle, and that's what we're going to use here. So if you could show that those two triangles have angles, two sets of angles that are congruent, you got it, right? And yeah, BCE, you're thinking? I did AD, and I'm saying CB. No, I did it right. This is what I want. Now, let's just talk about it. Can you see an angle congruent to another angle? Yeah. So this angle has to be congruent to this angle? Why? Yeah, but can you say why it is? We'd have to show the angles congruent before we show the triangle similar. So this is what I mean, guys. Everybody in here for Friday should see why those two angles are congruent because of a property of a circle that we've been studying. Okay, so for Friday, you'd have to know that result. And this should be an obvious thing. Yeah. They both are inscribed angles, and they both intercept the same arc, DB. See that? And so angle A is half the measure of arc DB. Angle C is half the measure of arc DB, so those two are congruent. And it's one of the corollaries we looked at. I think it's the overlapping one. If you go back, forget which one it was, but it's one of the results you need to know. Okay, it was right after the semicircle one. And so you can, and I'm sure you can come up with another set of angles that are congruent. You guys see another one? Vertical angles. And there you have enough to show the triangles are similar. And then once you show the triangles are similar, you could set up proportions, and I'm going to demonstrate that with the next two proofs to get the result. Okay. All right, so let's look at the next theorem. This one says if you have a tangent and a secant drawn from an external point. So you have this circle, you have some external point P here, and you got this tangent segment. Here's the point of tangent C, I'll call it point A. And you have the secant segment, maybe intersecting at B and C. And say we found the length from P to A, and that length is length X. And then we found the length from P to B and found that that was length Y. And then we found the length from B to C and found that that's length Z. So if you know those three lengths, there's a relationship between them. And what this proof is, or the theorem is saying, is that x squared is going to equal what times what? You read that theorem, or read what we're trying to prove, and tell me what x squared would be equal to. Y times, not z, not y times z. Well, it says the length from P to B, that's what? That's y. And the length from P to C, how long is that? Y plus z is that length. So it's y times y plus z. Right? That's what that's kind of what that's saying. If I knew those lengths. So we want to be able to show that that's true. All right. So I'm gonna write up a little proof for you guys. Okay. And so in this proof, my goal is to show two triangles are similar. And one of the triangles is what I'm outlining, this big triangle here. Okay. I want to show that that big one is similar to a smaller one inside of it that I'll outline in red. This one right here. Okay, so this is a little trickier. You have a big one to show, so the bigger one's similar to that smaller one. Can you see two angles that they share in common? Or an angle that they share in common? They both have what? Angle APB, or I'll just call it angle P. So we could say that angle P is congruent to angle P. I'll start there. And that's our reflexive, right? All right, we just need one more angle, and then we could prove similarity by angle. Now they've marked it out for us. They said this angle right here is the same as this angle right here. Can we argue why? And this is where you got to know some things about circles again. Okay, just do this. Before we make that jump, tell me what you can tell me about the measure of angle ACB. Anything about that angle? Yes. Half of the measure of arc AB. Right? Because it is an inscribed angle. And if you go back and look at theorem 8.7, it says that the inscribed angles have to measure the arc. What can you guys tell me about the measure of angle PAB? Anything about it? Yes, Elena. Yes, for a different reason. You remember what's the reason? Or which theorem? And you can look back. It came from our last lesson. It was the first theorem I proved. 16? Okay. So these are the results you got to know, because in this angle, it's an angle between a tangent segment and a secant segment. Sorry, not a chord. It's the angle between a tangent and a chord, and we learned that 1/2 the measure of that arc it intercepts. Okay. So now we could say, well, because those are both equal to the same quantity, well, then the measure of ACB is going to be equal to the measure of angle PAB by substitution. Okay. And because the measures are equal, we could say that angles are congruent. And that's a definition of congruent angles. So a little bit of extra work. I had to work a little harder to get my angle. So statement 1 and statement 4 is enough now to say that the triangles are similar. So triangle, let's see if we could do this right. Triangle CAP is similar to triangle what? Letter ordering matters here. BAP? P, no. Again. CAP goes with what? ABP is what we want. By angle similarity. And now that I have those triangles similar, I can set up a proportion because that's what it means to be similar, right? We have proportional sides. And so I'm going to kind of break off our traditional proofs format and just write a proportion. So side AP, so I'm gonna have the yellow fraction over here and the red fraction over here just to help you see the difference. Okay, so in this, on the left side, I'm gonna have AP be from the yellow side. Okay, so AP over, I'm still working with yellow, so I'm gonna go work with the full length from P to C. Okay, now for red, what would that be proportional to? AP would be similar to which side in the red triangle? And if you get confused, look at the ordering. A and P are the last two letters. So B and P are the last two letters, so it should be B and P. Okay, and then P and PC is going to correspond with what? PA or AP. All right. So now if I cross multiply, I get AP squared is equal to PC times BP, or sorry, PB. And that's exactly what I wanted. Proof done. All right, so that's kind of our similarity proof. And when you, with the previous one that you're going to do for homework, you prove the triangle is similar, and we kind of talked about how. Then you set up a proportion and cross multiply to get your result. Okay. Now we got one more result here. Last one. And then the last one for the unit as well. If we have a circle, an external point, and two secant segments, okay, and let's say the length from A to B is length x, the length from B to C is length y, from A to D is lowercase a, and from D to E is lowercase b. What is the theorem saying? What products can I put here in terms of x, y, a, and b? What times what equals what times what? No, it's not x times y is equal to a times b. That's not true. Read it carefully. says, you can even look at what we're trying to prove. We're trying to prove length from A to C. What would that be in our case? X plus y would be the length from A to C times AB, which would be times X, is equal to what? A plus B times A. That's what that proof is saying. Okay. And to do this, we're going to show two triangles are similar again. And I'm going to outline them for us in here. So one I'm going to outline in red. So this triangle here, I want to show is similar to this triangle that I'm outlining in green. Okay, you kind of overlap there. I want to prove that they're similar. I'm going to use angle-angle similarity. Can anybody tell me what angle is congruent to what angle? A is congruent to itself. Flexive property of congruence. Okay, I need one more angle. Anybody see what it is? Congruent to another angle? BCD is congruent to angle DEB. There's a corollary that says that. Find it. What is it? So one of our results. Because both those angles are inscribed angles and they share the same intercepting arc. Right? Which corollary is that? 8.9? All right. That's from corollary 8.9. All right, so then we have enough evidence to say that triangle CAD is similar to triangle EAB by angle-angle similarity. All right, so we got similar triangles. So now let's set up, I'm going to say red and green so we could see the difference here. Two proportions. So in the red, I'm going to say BA or AB over AE. Those are both coming from my red triangle. Would be that proportion would equal what from the green triangle? AD over AC. And so now if I cross multiply, I get AC times AB is AE times AD. Is that what we were trying to prove? Yep. Proof done. Okay. Okay, so now we're going to summarize these three theorems here. Do we remember? So in the first one, if we have intersecting chords or secants inside that circle with these lengths A, B, C, and D, what can you say? What's one of the results? A times B is equal to C times D, and that's the one that you're going to prove for homework. Okay. Type 2 is if we have intersecting segments that cross outside the circle, or secants, not segments, secants. What's true? A times what? A plus B is equal to C times C plus D. Okay. And then type 3 is if you have a secant and a tangent intersecting outside of a circle. What's the result here? A squared equals B times B plus C. Okay, so those are the three results that we are going to work with. Now let's apply them to some situations. Let's start simple. Number 1. Okay, so here we have two secants intersecting, and so we could say 10 times x is 14 times 5. Sorry, 14 times 15. Okay, and so then we could say x is 14 times 15 divided by 10. 14 is 7 times 2. 15 is 5 times 3. 10 is 2 times 5. So we can divide top and bottom by 2 and by 5. And we end up with 21 as an answer for x. Okay. So that's an application of the intersecting chords. Let's now skip down to number 5. Go ahead and solve for x in number 5. Okay, so on this one, 9 times what? 9 plus x, not 9 times x, but 9 times 9 plus x is equal to 8 times 8 plus 19. So that's 9 times 9 plus x is equal to 8 times 27. I could divide both sides by 9 and get 9 plus x is equal to 8 times 3. 8 times 3 is 24. And subtract 9 from 24 and get 15. Okay. I tend to try to divide instead of multiply. Because if you don't have a calculator handy, it's easier to work with smaller numbers than bigger numbers, right? But you can go the other direction too. All right, let's try to trick you guys a little bit, huh? Try number 10. Okay, so on this one, we should start by saying, well, 16 squared is 8 times 8 plus 5x minus 1. You guys start there? All right. Now, if I didn't have a calculator handy, I know 16 is 16 times, sorry, 16 squared is 16 times 16. And that's 8 times, well, 8 minus 1 is 7 plus 5x. So if you don't have a calculator handy, what would be a good next step? What do you mean factor? Okay, you could change 16 to like 8 times 2. But if I divide both sides by 8, good move, right? Because then I'm going to divide one of these 16s by 8 and divide that 8 by 8. And so I end up with 16 times 2, which is easier to work on, is 7 plus 5x. And so that's 32 is 7 plus 5x. Subtract 7 from 32, you get 25. And then divide by 5 and you get x is 5. But that's not Pn, so we still need to find Pn. So Pn is going to be 5x minus 1, which is 25 minus 1, which is 24. Okay. You could have also looked ahead and said, you know what? I just want Pn. I don't want x. So forget about that 5x minus 1. I'm just going to put a y there and solve for y. You could do that, right? How would that look? That would say, well, 16 squared is 8 times 8 plus y. And solve for y and you have the answer. Okay. All right. Well, I didn't trick you too much on that one. So I'm going to really trick you now. Try 13. So here we should have set it up. X plus 6 times x minus 1 is 12 times 10. Everybody start like that? All right, so we're looking for these two numbers. So if I multiply this out, I get x squared minus x plus 6x minus 6 equals 120. Did we go that far? Okay. Then I could combine like terms, get x squared plus 5x minus 6 is 120. So if we're thinking quadratic, which we have here, quadratic, then if we're thinking quadratics here, what is a good method to solve this quadratic? You got to make it equal to what? 0, and then try to factor it. So subtract 120 from each side. So x squared plus 5x minus 126 equals 0. And then remember when we factor, we ask ourselves, what two numbers have a product of negative 126 and a sum of 5? And it's not so obvious here, so we break down that number 126 to get its prime factors, right? So 2 and 63, 9 and 7, 3 and 3. And so we know just 126, positive 126 is 2 times 3 times 3 times 7. And so that gives us some factors to play with. 14 and 9. Which one's positive, which one's negative? So negative 9 and positive 14 add up to our 5 and multiply to negative 126. So now we found it, we can factor this to x minus 9 times x plus 14. And set each factor equal to 0 and solve, and you get x is 9. Or x is negative 14. We can't have two answers. So we got to throw one out. One of them is obviously wrong. Which one? Yeah, we're talking about length here. Negative 14 won't work for us. So x is 9. Woo! Okay, you want to be able to do that. Okay? I'm going to stop there. You have some homework problems like that and practice that. Okay? And only one theorem to do. Question is, get ready for that test. Yeah, stack the chairs. Thank you. Possibility. Have a good day.
A great day.
Well. Hey. So, you didn't do which one?
I didn't finish part one. And I was
I don't remember that. So, did you tell me when you didn't finish? You just turned it in.
yeah, it was alright.
Because usually with a test, if you don't, did you have the whole period? Okay. This first one. So you just were stuck on it. Is that what it was?
Yeah.
Okay. So yeah, with that, I don't let you go back and do that one just because um, it wouldn't be fair to other students. Like, because if someone left, they can, not saying you did this, but someone could potentially, oh, that's the one I didn't know how to do. Study up again and go back and do it, and it wouldn't be fair to others. So I can give you the other one though that you didn't do, and if you don't do well on it, we do give another retake. Okay. That work? Okay. You find it? Yeah, I didn't find it in this folder. So you did the first day, not the second one? It's in the last one. So for the Mo part. Cool. Take it. All right. Thanks so much. All right. Yeah.
Hi.
Hey. Finish it.